Hello everyone. My name is Suvrat and we'll be discussing CodeChef Starters 222. So let's start the discussion. So problem A is layered cake. So chef is making a layered cake consisting of two layers. Chef has n options for the first layer represented by an array A is equal to 1 A1 A2 till AN, where AI represents the size of the ith first layer of the cake. Similarly, chef has m options for the second layer represented by an array B equal to B1 B2 till Bn, where Bi represents the size of the ith second layer of the cake. So chef must ensure that the size of the second layer is strictly smaller than the size of the first layer. How many possible cakes can make by combining one first layer and one second layer while respecting that constraint? And the given problem are t is less than equal to 100 and n comma m also less than equal to 100 and ai comma bi also less than equal to 100. So the expected time complexity might be around O of n into m, because n into m into t would be around 10 to the power 6, which would easily pass. So problem A, basically chef has two arrays, A, which is of A1, A2 till AN, and B, which is B1, B2 till BM. And chef is trying to make a cake of which the size of the second layer is strictly smaller than the size of the first layer. So if this is the first layer, then the second layer must be strictly smaller. And also the m options for the second layer is from the array B and the n options from the first layer is from the array A. So basically this is some AI and this is some BJ, and AI, and we are given that AI and BJ make a suitable cake if AI is strictly greater than BJ. So basically, since the constraints are n less than equal to 100 and m less than equal to 100 and t also less than equal to 100, so we can run time complexity up to O of n into m into t. So since we need to count the pairs such that AI is greater than BJ, so basically what we can do is we can brute force over all the pairs from I equal to 0 till I less than n I plus plus. For j equal to 0, j less than m, j plus plus. And if AI is greater than bj, then we can maintain a count and increment it each time we check for a certain pair where AI is greater than bj. And in the end, we can just see out ct. So this will be time complexity O of n into m, and there are t test cases, so O of n into m into t, and that is around 1e6 operations, so it will pass. And I'll show you guys the code for this. So basically vector a and b, then I take input a and b, and then for each pair I check if ai is greater than bj, and if it is, then I increment the value of answer, and in the end I see out answer. So that was the solution for problem A. Is this div 3 or div 2? This is div 4. Got it. Well, the questions would be same over all the divisions, and I am currently discussing div 2. Actually, the questions are same, so doesn't matter I'm discussing div 1 or div 2. Basically, this was the first problem in div 2, and then the problems would be these four. So I'm basically discussing D2 from the first problem. Now let's move on to the second problem. So the second problem is sorting prefixes. You are given an array A, which is a permutation of the integers 1 comma n. That your task is to sort the array using the following operations as many times as you want. So the operation is choose an index I and then pay AI coins to sort the prefix A1 to I of the array. Note that the cost is levied before the sorting operation is performed. Here A1 to I represents the prefix A1, A2 till AI. What is the minimum total cost to sort the array? And the given constraints for this problem are t is less than equal to 100, n is less than equal to 100, and ai is from 1 till n. So basically the expected time complexity of again this problem could be around O of n square for each test case, because O of n square into t would be 10 to the power 6 operations, which would pass easily. So problem B. So in this problem we are given an array A, and what our goal is to basically sort this array. And we can use the following operation to sort this array, and the operation is basically that we can pay ai coins to sort a from 1 till I. So basically we can use this operation multiple number of times, and we need to basically tell the minimum cost of sorting the array. So that would be our problem. So let's see the test cases for this. So the first test case is 1, 2, 3, and since this is already sorted, so we don't need to perform any operations. So the number of operations would be, and the cost of operations would be 0. Then the next array is 3 to 1. Next test case is 3 to 1. So 3 to 1. So basically, initially we can perform 3 different operations. Either we can choose to sort the array till here, that would be cost 3, or we can choose to sort the array till here, that would be cost 2, or we can choose to sort the array till here, and that would be cost 1. So obviously we can see that we are paying more cost and sorting a small portion of the array. So instead of doing that, we can just pay a single coin and sort the whole array. So we'll be choosing this operation, and after performing this operation, the array would become sorted, and hence the minimum cost of sorting this array would be 1. Let's see the next test case. It is 2, 3, 1, 4, 5. So 2, 3, 1, 4, 5. So now we can see that we have multiple different options here. So we can either sort till here, or we can sort till here, or we can sort till here, or we can sort till here or here. So obviously one of the ways to sort the whole array would be to sort it in a single operation using this 5. So basically the cost would be 5, and the array after sorting will become 1, 2, 3, 4, 5. But what we can observe is that these 4 and 5 remained in their position and didn't actually need sorting. So we might actually get a better cost. So basically what we need to do is actually sort the array till here only, because 4 and 5 are already at the correct positions. So we need to sort the array till here. And so basically again our problem is just like the last problem, where the last element is 1, so we'll prefer using that operation over the other. So we will, instead of doing the 5 operation, we'll do this operation, and our array will become 1, 2, 3, and 4 and 5 will remain at their positions. And since this array is sorted, so this will be the final result, and the cost of this operation would be 1. So 1 would be the answer for this test case. Now let's see the next test case. So next test case is 2, 1, 4, 3, 5, 6. 2, 1, 4, 3, 5, 6. So again, we can see that 5 and 6 are at their sorted positions. So we need to basically sort this much array. So there is no point in including these two numbers in the operation. So basically now we have multiple different choices. Since here is a 1, what we can do is basically sort this much of the array for a cost of 1, since that is the minimum cost, and that would make the array 1, 2, 4, and 3, 5, 6. But still, this 3 is out of place and this 4 is also out of place. So we will need to perform either this or this operation. So if we perform any of these two operations, what will happen is basically uh, we would notice that we have already wasted this operation. Actually, if we had performed this operation, we don't actually need to perform this operation. So what I'm saying is, let me write it more formally. If we are performing operation till the ith index, any operation performed before it, any operation performed for index, actually not before it, for index j less than I is waste. Since if we perform an operation till the ith index, all the numbers from a1 till ai would be sorted. So actually performing an operation on index j which is less than I is a waste, because that would only be sorting the array from first index till the jth index. So that is not something we want. We want the array to be sorted because we've already sorted till the ith array, right? So instead of performing two operations on the jth and the ith index, we could only perform the single operation on the ith index, and the result would be the same for both the cases. So it is more optimal to perform the operation on the higher index. So let's say that upon performing some operations on index a1, a2, and a some x. So let's say that I'm performing on operations on the indexes a1, a2 till ax, and the order of these indexes are this. So basically, because of this observation, what we can say is we don't need to perform the operations on these indexes, and only performing the operation on ax index would be sufficient. And actually, if we need to perform the operation on ax index, if on the xth index the value is not set to its correct position, then we will have to perform the operation on the xth index, because we can see in this test case, we can notice that 6 and 5 were at their correct position, so we need not include them in any operation. But 3 was not in its position, so we need to do some operation that has an index which is greater than index of 3, because we need to include the 3 in any one operation so that the 3 gets placed to its correct position. So we will at least need to perform an operation till this index. And what I'm saying is that if we are performing an operation on this index, we will not we won't want to perform any operation on any index lower than that. So basically now we have options to perform operations on these indexes. And obviously, since these two are at their correct positions, so they must be greater than 3, right? Because these two are the largest and the second largest elements in the array. This if the last element is at its correct position, then it must be the last element, and if the second last element is at its correct position, then it must be the second last element. And obviously 3 would be less than or equal to those elements only. So again, we can reduce our optimality of operation to just this index, and hence we'll be able to conclude that we only need to perform operation on the last index which is not on which the value is not correct. So let me take a general case and explain this again. So let's say that I have this array, and let's say that some of the last values are set correctly. That means they are equal to the final value that must be at that place, that must come at that place. And then, so that must mean that this value is not at its correct place. So what I'm saying is that if we are performing any operation before this index, so that will not set this index to its correct position, right? So we will at least have to perform an operation till this index. So what possible operations we would have is this operation or any index further than this. And now to choose any one from these, we can say that since these last elements are already set at their correct position, so they must be the largest, second largest, third largest of the array. So it is not optimal performing operations using those values. And this must be strictly smaller than those values, or strictly less than or equal to those values. Otherwise, it must come at somewhere here, and then because of contradiction, we can say that these elements would not have been set correctly. So if these elements are set correctly, this element must be less than or equal to those elements. So we need to at least, so we can perform operation on this index. And since we are performing an operation on this index, we don't need to perform operation on any of the smaller indexes, because this index will sort all of this array and these elements are already sorted. So basically, what we can do is we can make two arrays. First array A is the input, and then we can make another array B, which is just A but sorted. And then we can find the last index I, which for which AI is not equal to BI, and then answer will be AI. So obviously, to find the last index on which they are not equal, we can just run a simple O of n for loop from the starting from the last index and going backwards. So that would be O of n time complexity, which is well within the time limit. So I'll show you guys the code for that. So basically, I take input vector A and vector B. Initially, vector A and B would be same, and then I'll just sort the vector B. And then what I can do is starting from the n minus 1th index till 0th index, I'll go backwards, and if AI is not equal to BI, then I know that I'll have to perform the operation on this index, and this would be the most optimal optimal operation. And I can just do answer is equal to A of I and break out of this loop, and in the end I can just see out answer. And if the array is already sorted, then it will not break out of this loop and answer will remain at 0. So that was the solution for problem B. If you guys have any doubts, you can ask. I checked from the last and the cost in the index where the array is not sorted from the last, but it didn't work. Cost is not the index. Cost is the value at that index. What is the proof mainly? Please explain again with some test cases. Basically, the proof is that first of all, there is this observation. If I am performing operation on the ith index, then in no case I will perform another operation on index j less than I. Do you understand this observation, Sheikh Rafi? Just check the number from the last of the array, check where the ideal order missed, and print that index value of the array. Yep, that is right. Checking only sort from the back won't work. You have to check AI equal to I plus 1. And what is that? For int I is equal to 0, I less than an I plus plus. So you get that, right? So what I'm saying is that we will only perform only, so based upon this observation, we can say that we will only perform one operation. Because if I am performing two operations, if I am performing two or more than two operations, then all the operations except the highest one would be waste, right? You get that, Sheikh? So we will be only performing just one single operation in the optimal case. Okay. So now we will perform only one operation. So what indexes we can perform one operation to get the whole array sorted? So obviously the initial thought would be that we need to perform on the last index only, because only then the whole array would be sorted. But what if some of the last positions are already at their correct places? So basically, let's say in the example 2, 3, 4, 1, 5, 6, the actual sorted array would be 1, 2, 3, 4, 5, 6. So we can see that 5 and 6 were already at their correct positions. So we need not perform operation till here. What we can do is we can perform operation till here only. So we need to choose one out of these indexes to perform the operation on, and we can choose the minimum out of that. So obviously one thing you can do is you can just go from the last index and go till here and take the minimum of all of them, and that would be the answer. But you actually don't need to take the minimum of all of them, because 5 and 6, if we are saying if they were at the correct position, that would mean that 6 was the highest in the array and 5 was the second highest in the array, and 1 would have to be less than or equal to those two. Because if 1 had been greater than it, if any one of them, then their correct place could not have been this. 1 would be coming between them and their correct place would be different. So if 5 and 6 are at their correct place, all rest of the elements would be less than equal to 5 or 6. So that is why we can conclude that we only need to perform the operation on this index. Now do you get that? Shake. Okay. So let's move on to the next problem. I don't think you guys have any more doubts. So the next problem is set up to 2. Oh, okay. I think I did not. Did I? I showed the solution, right? So the next operation is sell up to 2. There are n days, and the sell price of a watch on the ith day is AI. Initially, you have 0 watches. For each day from 1 to n, the following events happen. First, you acquire 1 watch for free on each day. Next, you may choose to sell up to 2 watches for AI coins each. What is the maximum profit you can obtain by optimally selling items? And the test cases and the constraints for this problem is t less than equal to 100 and n less than equal to 100, and AI is still 1e7. So the expected time complexity for each test case would be around O of n square, because then the overall time complexity will become O of n square into t, which is 10 to the power 6 operations, and that would pass. So we are given this problem C. So basically for each day from 1 to n, these two events happen. So for each day 1 to n, two events happen. The first event is that we get a watch, we get a free watch. And the next event after this, after the first event, this events happen, is that we can sell at most 2 watches at the price AI. So basically we can understand this if we look at it like this. So let's say I had W number of watches, I had W watches on day I, on the start of day I. So basically after the first event, after event 1, I will have W plus 1 watches. And after this, in event 2, what I can do, I will have 3 different scenarios. Either I could have chose to not sell any watch, so in that case I will still have W plus 1 watches. In the case where I just sell one watch, in that case I will have W watches. And in the case where I don't sell any watch, in the case where I sell two watches, I will have W minus 1 watches. And in this case I will have AI coins extra, and in this case I will have 2 into AI coins extra. So that is the problem. So basically, if on the ith day I have W watches, then first of all I'll get a free watch and it will become W plus 1 watches, and then I can choose to not sell any watch on that day. So on the next day I'll go with W plus 1 watches, or I can choose to sell one watch on that day. So on the next day I'll go with W watches plus I'll get AI money. And if I choose to sell two watches, then on the next day I'll get W minus 1 watches and 2 into AI coins. So that is the problem. Let's see the test cases. So the first test case is 1, 2, 3. 1, 2, 3. So on the first day, I get one watch. So obviously, what do you guys think I should do? I will obviously not sell any watches on this day because the price is so low. I'll get better offers on the next day and the day after that. So what I can do is I'll retain the watch, and on the next day my watch will become two, since I'll get another free watch on the next day. And now I have the option to sell watches. So if I don't sell watches, I'll go to the next day with three watches. And having three watches is not good because then I'll have to waste one watch, because at max I can sell two at this index, right? So I'll be wasting one watch. And also, so basically, what I'll do is I'll sell one watch here to get a plus 2 coin, and then on the next day I'll have another free watch, and then my total watches will become 2. Basically, on the day 1 I chose this event, and on the day 2 I chose this event. Day 1, day 2, because obviously then I'm selling my watches with the highest price. So then I'll have a plus 6 coin, and I'll go on the next day with 0 watches. So on the day 3, I am performing this operation. And since the total number of coins I'll get is 8 coins. 8 coins. So what we can do is, basically, the constraints tell us that the maximum number of coins that we will have on any particular day is 100, right? Because you can acquire only one watch, only one free watch on each day. So the maximum number of watches would be 100. And since we have three different events that can happen on each day, so what we can do is we can use these events to write some kind of DP. So this since these events will work as the transition between states. So let's say at the ith day I had W watches. So on the I plus 1th day, what are the possible different outcomes? So I might have W plus 1 watches, or I might have W watches only but extra AI coins, or I might have W minus 1 watches plus extra 2 AI coins. And since there are n days, so I will be less than equal to n, and since at max we will have n watches, because each day we get only one free watch, so W will also be less than equal to n. So the total number of states in this DP, the total number of different states would be n square. And each state depends on only 3 other states. So basically our total time complexity will be, so there is a formula for time complexity of DP, number of states into transition, average transition per state. So since there are 3 average transitions per state, so overall time complexity would be n square into 3, and that is well within the time limit. So basically, I'll tell you guys this, that in problems that require DP as a solution, you can guess that from the constraints. Constraints give us a lot of hint towards DP solutions, and yeah, it is not true every time, but it works in a lot of cases. And also, in some questions where you don't see any kind of greedy approach working, and if the constraints you see are like small enough for DP, so you can think towards DP. So I'll explain how you can further build the solution. So what we will do is, in order to find the answer for the test case I comma w, since we want the maximum coins for each state, right? So the answer for the case I comma w would be a maximum of three different states: I plus 1 comma w, just a second, I plus 1 comma w plus 1, or I plus 1 comma w plus ai, or I plus 1 comma w minus 1 plus 2 ai. So basically, this means that this represents the number of coins I will get if on the I plus 1th day I have w plus 1 coins. And this represents what the number of coins I'll get if on the I plus 1th day I have w watches. And this represents if on the I plus 1th day I have w minus 1 watches. And since I sold 2 watches, therefore 2 into ai extra coins. And since I already sold 1 watch, so ai extra coins. And so for each DP we require a base case, and we can see that from I we are moving towards I plus 1. So in the end we will be reaching I equal to n. So we must write our base case as I is equal to n. So what we can do is, if I is equal to n, we can just simply return 0, because we cannot sell any more watches now since we have already ended the number of days. So why I equal to n? Because basically I am assuming that the indexes are 0 based. So I equal to n would be the n plus 1th day, and on that day you won't be able to sell any watches. So we can say that if I am at the n plus 1th day, I can now earn only 0 coins. So if I is equal to n, return 0, and for all the other cases we can take a maximum of these two. And also the watches, the count of watches must never go negative. So for this particular transition, we also need to add an if statement. We can only run this transition when w is greater than 0. Otherwise, if w is equal to 0, then w minus 1 will become negative, and that is not possible. We cannot have a negative number of watches. So w must be positive for this particular transition. And overall time complexity we already discussed, and the answer for the question would be simply the state 0 comma 0, since on the 0th day we start with 0 watches. Actually, on the first day we start with 0th watches. So I'll show you guys the code for this. So basically this is my DP, and this is the first transition where I'm selling two watches on that day, or the second case where I'm selling just one watch, or the third case where I'm not selling any watches. So if I sell one watch, ai plus dp I plus 1 comma watt, 2 ai plus dp I plus 1 comma watt minus 1, and the third case is dp I plus 1 comma watt plus 1. And this is for DP memoization, and this is the base case. And in each test case I am setting all the states from 0 till n and 0 till n dpij as minus 1, so that I can memorize perfectly. And then in the end I'm doing cout dp 0 comma 0, because that state corresponds to the maximum money I can earn if I am at the day 1 with 0 watches. So that was the solution for problem C. If you guys have any doubts, you can ask. I'll be back from washroom, guys, so you can ask your doubts if you have. Um, so I mean, it's a simple DP kind of knapsack, so pretty easy only. Yo, the GCD question was a actually the thing about GCD question is that in my division in Div 1, like almost only half the people who solved ascents and descents could solve GCD limit. And also I couldn't solve GCD limit during the contest. So it might be possible that because in Div 2, I think a lot of people solved GCD limit. Yeah. So in Div 2, a lot of people solved GCD limit. So I don't know. I can't comment on that because I don't have any proofs. But yeah, might be. So how we get comfortable with DP questions? Which problems we have to solve for practice to get better understanding? Um. So basically, in DP, first of all, you need to know about some of the standard problems like knapsack, frog jumps, and stuff like that. Basically, the AdCoder DP questions or the CSCS DP questions. You need to solve the basic problems from those so that you get to know how DP actually works. First, you need to understand how DP actually works, and then comes the thing that when you encounter a problem, now how do you know if DP could be applied to this problem or DP can't be applied to this problem? So first of all, let's not focus on the constraint. I'll tell you how I decide whether DP can be applied to a problem or cannot be applied to a problem. If let's say that constraints were not a problem. So basically, let's talk about this problem only. So DP is kind of a brute force only. DP is kind of brute force. In this problem, what we were asked that each day we get a free watch. So obviously, if I have W watches, I'll have W plus 1 watches at the start of each day. And then we have three different choices. We have three different choices to do. We can either sell 0 or we can sell 1 or we can sell 2. So two important points that we can note here. First of all, 3. 3 is a small number. So why do we have a small number like 3? Why not we can sell up to some array that is given to us? Why not we can sell up to BI or we can sell up to some 1E5 or some bigger number? Why 3? So this 3 is a hint towards DP, because in DP we can only have a small number of transitions. We cannot have a large number of transitions because that would be TLE. So this 3 would be a hint towards DP. And then the next case is that all the three different paths that we can take lead us to a pretty similar kind of state. Basically, what we started from, we again have a very similar kind of state. Basically, we had on the ith day W watches, and then now on the I plus 1th day we have some W or W minus 1 watches. So we have a similar kind of state. So we can see that if I need to solve this problem, what if I know the answers to this problem already? So if I know the answers to this problem already, then we can start seeing these problems as sub problems to this bigger problem. So we can see that bigger problem has three different sub problems, and that is another hint towards DP. Now there are a lot of questions that would get solved by DP if time limit was not a constraint, because here we are not applying any greedy observation, or here we are not doing any analysis of something like binary search or whatever. We are not making educated choices on each day. We are basically we are trying all the three choices on each day, and then we are seeing what is the best choice. So this is not always optimal in every problem. So there might be some state that would give you the answer if you use DP on those states, but those states might be might not fit in the given time limit. It might be n square in a problem where n is 1e5. So then you will have to think about some other way that you can either reduce these states, or you can make any observation and apply some kind of binary search or some kind of greedy, where you can pick one of the choices and leave out the rest of the choices. So that's how you can differentiate if a problem could be solved by DP or could not be solved by DP. If you are able to differentiate using some greedy or other binary search like logics, then you don't need to use DP. So also there might be some problems where you actually need to apply binary search on the DP states, but you'll encounter them in slightly harder problems. You will encounter these solutions in slightly harder problems, and at that time you will be ready for that. So if my so actually the best advice is, just if you are struggling on DP, you can just go practice on different platforms for DP problems. If you're struggling on binary search, you can practice binary search. If you're struggling on greedy, you can practice greedy, and you'll see the difference. You'll start seeing the problem as a state only if you practice DP well enough. You'll not even have to think about that. So I think that answers the question. I'll wait for a minute. If you guys have any doubts, you can ask. Then I'll move on to the problem D. Okay. Hey Suvrat, can you tell me how you writing on screen? Is it a drawing tablet and software name? So I basically use a drawing tablet or by Wacom, and the software name is Rnote. Rnote. So yeah, you can check it out if you want. So I think I'll move on to the next problem now. So the next problem is ascents and descents. So ascents and descents for a permutation P of the integers 1 to n, let Q be the unique inverse permutation of P. That is Q of Pi equal to I. So define f of P is equal to summation I is equal to 1 till n minus 1, Pi less than Pi plus 1, plus summation I is equal to 1 till n minus 1, Qi is greater than Qi plus 1, where this is 1 if x is true and 0 otherwise. In other words, f of P is the sum of number of ascents in P and descents in Q. Given n and k, your task is to find the permutation P of the integers 1 till n such that f of P is greater than equal to k. And also, this is a kind of special problem. There are only two test cases in this problem. First test case, we are already given that n equal to k 6 and k is equal to 6. That is the sample test case. And the second test case, we are given that n is equal to 10 to the power 5 and k is equal to 1.99 into 10 to the power 5. So we actually kind of only need to solve for this test case. This test case, we already have the answer, which is this. And the constraints is that only. So expected time complexity would be O of n, because n is still 1e5, right? So O of n or O of n log n at max. So problem D. So let me write the constraints. For n is equal to 1e5 and k is equal to 1.99 into 10 to the power 5, we need to find a permutation of n for which f of p is greater than equal to k. And now let's see the definition of f of p. So f of p is nothing but summation from I is equal to 1 till n minus 1, p of I is less than p of I plus 1, plus summation from I is equal to 1 till n minus 1, q of I is greater than q of I plus 1. And obviously, this represents 1 if true and 0 if false. So we just need to actually count the pairs where pi is less than pi plus 1 and qi is greater than qi plus 1. So now what p is basically the permutation that we are talking about, and let's see what is q. So q is the inverse of p. Q is the inverse of p. What does that mean? Q of pi is equal to I. Basically q of pi is equal to I. So let's see a sample test case for better understanding. So we have given 6, n equal to 6 and k equal to 6. So n equal to 6 and k equal to 6. And the output for this test case is 245136. 245136. So let's first let's assume that this is p and let's try to write q. So q have 1 2 3 4 5 6 indexes. So now we know that q of pi is equal to I. So q of p1 is equal to 1 and p1 is 2. So q of 2 is equal to 1. Then q of p2 is equal to 2 and p2 is 4. So q of 4 is equal to 2. Then q of p3 is equal to 3. So q of p3, which is 5. So q of 5 is equal to 3. So q of 5 is equal to 3. Then q of p4 is equal to 4. So q of p4 is equal to 4. So q of 1 is equal to 4. Q of p5 is equal to 5. So q of p5, which is 3, q of 3 is equal to 3. Q of 3 is equal to 5. Then q of p6 is equal to 6 and q of p6 is 6. So q of 6 is equal to 6. So that way we can get the array. Also, another way you can look at this is 2 has the index 1 in p, 1 2 3 4 5 6, and basically what we are doing is we are writing 4 at the first index, then we are writing 1 at the second index, then we are writing 5 at the third index, then we are writing 4 at the second index, then we are writing 3 at the fifth index, then we are writing 6 at the sixth index. So basically 1 at the second index, 2 at the fourth index, 5 at the third index, and that way, and like that. So basically q of pi is equal to I. Now let's count the value of f of p for this array. So here, since 2 is less than 4, we will get 1 point. 4 is less than 5, we'll get another point. And 1 is less than 3, we'll get a point. And 3 is less than 6, we'll get a point. So 1, 2, 3, 4 points from this summation. And then another point here, another point here. And that's it. So 2 points from this summation, 4 and 2. So overall there are f of p is equal to 6. And since it is greater than equal to k, so we got the answer. So that was it for the test case. Now let's analyze this statement a little further to get the solution. So we have f of p as summation I is equal to 1 till n minus 1. Pi is less than pi plus 1 plus summation I is equal to 1 till n minus 1. Qi is greater than qi plus 1. So let's talk about we will get a point if pi is less than pi plus 1, right? So basically let's say that this was the ith index and this was the I plus 1th index, and here we had the value pi and here we had the value pi plus 1. So if pi is less than pi plus 1, we get 1 point. And the other condition is qi if greater than qi plus 1. This is the ith index, this is the I plus 1th index. So for this we get 1 point. So this is kind of straightforward. We need to analyze this a bit more because it is hard to visualize this, right? We are given this definition that q of pj is equal to j, right? We are given this definition. So q of I, let's assume that q of I is equal to some k. So what is k? So basically p of j will be equal to I, right? If we compare these two, p of j will be equal to I and k is equal to j, right? Let me, if we compare these two, p of j is equal to I and k is equal to j. So basically using these two, we can say that p of k is equal to I. Since k is equal to j, we can say p of k is equal to I. And that is simply in words. Let me write this in words. So k is the index of I in P. K is the index of I in P. So basically, if let's say this is P, then if we are talking about 5, then K will be 3 because 3 is the index of 5. So K is the index of J. So K is the index of I in P. So basically, if I am saying that for Qi is equal to K is the index of I in P. We can write this in words like this. So actually, to understand this more, what we can do is, we are given Qi is greater than Qi plus 1. So let's write Qi as K and K is the index of I in P. So we can write this statement as index of I in P is greater than index of I plus 1 in P. So if this is true, then we get 1 point. Right. Now this looks a little bit less confusing than Q, because here we understand what exactly gives us a point, and this other statement is quite straightforward already. So let me write these two conditions again. So first is that P of I is less than P of I plus 1. For this we get 1 point. And the next condition is that index of I in P is greater than index of I plus 1 in P. So this also gives us 1 point. So if we try to translate this in even easier words, what this will translate to is simply that I comes after I plus 1 in P. So basically index of I in P is greater than index of I plus 1 in P. So basically if I plus 1 comes somewhere here in the permutation, then I will come after it. Only then index of I will be greater than index of I plus 1. So we can write this as I comes after I plus 1 in P. Right? So we get 1 point if Pi is less than Pi plus 1 and 1 point if I comes after I plus 1 in P. So what we can do is, let's say that 1 comes after 2. Only then we'll be able to get a point from 1 and 2. Because if 1 comes before 2, if 1 comes before 2, then no point for us, right? So let's say that 2 comes before 1, so we'll have a point because of this pair. And let's say that 3 comes before 2, so we'll have a point because of this pair. And let's say that 4 comes before 3, so we'll have a point because of this pair. We'll have a point because of this condition. But if we try to look at this condition, so if we write an array like this 4 3 2 1, we'll actually not get any point because of this condition, Pi is less than Pi plus 1. And since in the constraints this k is quite large, this k is almost 2 into n, right? So we actually can't be so irresponsible with points. We actually need to get point on each and every index almost, because this is almost 2 into n. We need to get a point on almost each index. So we cannot actually do this. So what we'll do is we do need the points from Q also, right? Because we cannot actually use only the points from this equation, because we can get a maximum of n minus 1 points only. So we will actually have to use this equation as well. So we will have to place 4 before 3 and 3 before 2 and 2 before 1. But how do we place them so that we can enjoy these points as well? So let's try that. So let's say that I place 1 here, and then I place 2 afterwards, and then I place 3 afterwards, and I do this till x. So basically, because if I did this till n, then obviously that would be stupidity, because that would just make this array n minus 1, n minus 2 till 1. And now I don't have any points from this equation, because this is a strictly decreasing permutation. So we don't want to do that. So what we'll do is we'll stop at some x. So now currently for 2 and 1 we have a point, for 3 and 2 we have a point, and similarly till x we have 1 point from each using the Q equation. Right. Now where to place x plus 1? So what we can do is we can place x plus 1 either here, so that after x, basically there is gaps between 1, 2 and here x and x minus 1. There are gaps where we will fill the values so that we can get the points from increasing also, from pi less than pi plus 1 also. So now to place x, we have two options. We can either place x minus 1 here, or we can place somewhere here or here or here. So the thing is, to actually enjoy the point, sorry, x minus 1, not x plus 1. X minus 1 already has been placed somewhere here. We have 1, then we have some gap, then we have 2, then we have some gap, then we have 3, then we have some gap. Similarly, we have x minus 1 here, and we have some gap, then x. Now we have to place x plus 1. So we have two choices. We can either place x plus 1 just before x. We are saying that we are not placing x plus 1 after x, because we are limiting our increasing till x only, so that we will enjoy x minus 1 points from the second equation, this equation, because index of 2 is less than 1, index of 3 is less than 1, and similarly index of x is less than x minus 1. But then if we place x plus 1 here, then we will actually have to place x plus 2 here to enjoy the point from x plus 1 and x plus 2, because we need to place x plus 2 after x plus 1, right? Basically before x plus 1 in the permutation. But then what we are doing is this pair will become bad because x is less than x plus 2. So it is actually better to put x plus 1 here, so that I can put x plus 2 here and x plus 3 here, so that this pair is also increasing, this pair is also increasing, this pair is also increasing, and also x plus 2 is before x plus 1, x plus 3 is before x plus 2. So this is quite optimal, we can see. And here after x I'll place 2x. So let me demonstrate what I've done till now. So I've basically created an permutation where I have put 1 here, 2 here, 3 here, and add after and some number x here, and then x plus 1 I have put just before 1, x plus 2 I have put just before 2, x plus 3 I have put just before 3, and 2x just before x. And now what I can do again is I can put 2x plus 1 here, 2x plus 2 here, 2x plus 3 here, and 3x here, and some points similarly following this pattern here. So what happens if we write a permutation in this specific pattern? Let's analyze the different points. Let's analyze how many points we get. So basically, let me divide this into segments. So first we have x, 2x, 3x till the last number n. So let's write this as n upon x into x. Then in the next segment, we have then we have some segments, and then we have the 3, x plus 3, 2x plus 3 till wait, just a second, n by x minus 1 into 3, n by x minus 1 into x plus 3. And similarly for 2, and in the end 1x plus 1, 2x plus 1, until n by x minus 1 into x plus 1. So all of these have n by x terms, and there are 1, 2 and x segments like these. So for each segment, what I can say that because of the property pi less than pi plus 1, so this is less than, this is less than, this is less than this, I get for each segment I get n by x minus 1 points, right? So, and since there are x segments, so n by x minus 1 into x total points from this condition, and then we have this condition as well, that index of I in P is greater than index of I plus 1 in P. So we can see that index of 2 in P would be greater than 1, index of 3 in P would be greater than 1, and similarly index of x in P would be greater than x minus 1. So we can see that they form a sequence and they form a sequence. X and x plus 1 break the sequence because x plus 1 comes after x, and so that will not give me any points. So in each sequence there will be x minus 1 points, because 1 and 2 will give a point, 2 and 3 will give a point, and x minus 1 and x will give a point. So x minus 1 total points. And since there are how many sequences? N by x. Since this is 1 into x, 2 into x, 3 into x, till n by x into x. So there are n by x sequences. So this will be the total number of points that I get from a arrangement like this. So let's calculate this. So n by x into x would be n, then minus x plus n, then minus n by x, and this would be 2n minus x minus n by x, and 2n minus x plus n by x. And we have the constraints as n is equal to 1e5, and this is the value of f of p that we have generated, and we want f of p to be greater than equal to 199000. So what we can do is, let's just put the values. So this will become 2e5, actually let me write 200000 minus x plus 200000 upon x should be greater than equal to 199000. So 1000 should be greater than equal to x plus 200000 upon x. And also another condition is that x should be a divisor of n. Only then we will be able to make this kind of sequence easily, make this kind of permutation easily, because then all these numbers will be integers. So if we see the minima of this value, the minima of this value will occur at square root 200000, and obviously that is not an integer. So we can check for integers that are divisor of 2e5 near that value, and we'll get that x equal to 500 fits perfectly. Oh, my bad. Actually, n was 1e5, right? So this is 1. This is 1. Sorry. This is 1. So if we put x equal to 500, this value becomes 500 plus 100000 upon 500. And this is 200. So this becomes 700, which is less than or equal to 1000. So we are actually good to go with the value x equal to 500. So what we can do is, we can put the value x equal to 500 in this permutation, and we'll get the final answer. So let me write that again. So we have this permutation, x, then 2x, then 3x till n. Before that we have x minus 1, 2x minus 1, 3x minus 1, n minus actually n by x minus 1 into x minus 1. So yeah, don't confuse yourselves with this. It is just there will be n by x numbers in this sequence, and each will be plus x of the last number. Simply that. And the permutation is like this. After this n, it starts from this index, and after this it will start from this index, and so on. We will have the last, which is 1, then x plus 1, then 2x plus 1, and so on. So we can easily generate this permutation. Basically, we'll run a for loop for I is equal to x, which is this, till I greater than equal to 1, I minus minus. So we are for looping on the first numbers, and then we can again run another for loop. J is equal to 0, j is less than n by x, j plus plus, because there are n by x numbers in each segment. And then we can simply do cout I plus j into x. That's it. Because it would be x, then 2x, then 3x. For 1, we can see that it would be 1, then 1 plus x, then 1 plus 2x, then 1 plus 3x, and that's so on. So this will simply generate me the permutation, and overall time complexity would be O of n only, since there will be O of n numbers cout, because it is a permutation of n numbers. So that will be the solution. I'll show you guys the code. So for n equal to 6, I just have this special case written here. And then I'm putting x is equal to 500 and simply running a for loop from x is equal to I is equal to x till I greater than equal to 0, I minus minus. And j is equal to 0, j less than n by x, j plus plus, and I plus j into x. So that is the solution for problem problem D. If you guys have any doubts, you can ask. So I'll wait for a minute. Okay, so I think I'll move on to the next problem. So the next problem is GCD limit. So in this problem, for a sequence A is equal to A1, A2 till AN, we define f of A in the following way. Let Pi is equal to GCD A1, A2 till AI. F of A is equal to number of indices I, 2 till n, such that Pi not equal to Pi minus 1. And given an integer m, define g of n as the expected value of f of a when a is uniformly randomly selected among all m to the power n arrays satisfying the following conditions, that length of a is equal to n, and 1 is less than equal to ai is less than equal to m, And basically we need to find the limit n tending to 0 g of n modulo this number. And we have said that it is a rational number, so we'll be able to find the modulo easily. And for each test case we need to output the value of limit n tending to infinity g of n modulo 998 whatever. And the constraints for this problem is t less than equal to 1e3 and 2 less than equal to 2 is from m is from 2 till 2e5, and the sum of n over m over all test cases does not exceed 2e5. So because of this particular constraint, the expected time complexity for this problem would be around O of m or O of m log m, because more than that would not fit inside the time limit. So that will be the expected time complexity. So problem E. Here we basically need to find limit n tending to infinity g of n mod whatever, let's not care about mod, that is secondary. And what is g of n? G of n is the expected value of f of a. And what is f of a? So f of a is the number of indices I such that pi is not equal to pi minus 1, where pi is equal to the GCD of a1 a2 till ai. So basically let me first explain you guys f of a. So what is f of a? F of a is nothing but we have an array a, and let's say till the ith index the GCD of all these elements is p of I, and till the I plus 1th index GCD of all these elements is p of I plus 1. So if p of I is not equal to p of I plus 1, then for all such points, the count of all such points, let me write that, count of all such points will be f of a. So actually let's understand this a bit more. What exactly is p of I not equal to p of I plus 1? So what is so there is this property of GCD. So GCD of a comma b comma c is nothing but the GCD of a comma b. Sorry, let me write it like this. So the GCD of a comma b comma c. So how can we say this? So basically the greatest common divisor of a, b and c would also be the greatest common divisor of a, b, and with that the greatest common divisor of c. So basically whatever is the greatest common divisor of a and b, we take the greatest common divisor of that and c, and obviously we'll get the greatest common divisor of all three, a, b and c. So using this property, what we can say that p of I plus 1 is nothing but GCD of p of I comma a of I plus 1. And since we need to count all the points such that p of I plus 1 is not equal to p of I, so we need to count all such points that GCD of p of I comma a I plus 1 is not equal to p of I. And obviously we can say that the GCD of P of I comma AI plus 1 will be less than or equal to P of I, because GCD will decrease, right? If we take greatest common divisor of two numbers, it would always be less than or equal to both the numbers, obviously, because it is a divisor. We are taking the greatest common divisor. So we can say that GCD of Pi comma AI plus 1 is less than or equal to Pi. And also we can say that GCD of Pi comma AI plus 1 is a divisor of Pi. Now this is obvious, since we are taking the common divisor of Pi and AI plus 1, GCD of that will be a divisor of Pi. So now what we need to do is we need to find the expectation of f of a, where a can be any array of length n and ai is from 1 till n. Actually, if we do this of length infinity, then we can say that this is simply equal to the answer, since we need to find the value when the length is infinity. So answer is nothing but the expectation of f of a, where a can be any array of length infinity and this. So first of all, first things first, that if length is infinity, GCD of full A1, A2 till A infinity will always be 1, right? Because there are infinite numbers. At some point, the GCD would get reduced to 1. Since there are numbers are not ending, so at some point the GCD will have to become 1. So we can assume that the GCD, uh, we can assume that the GCD is 1 only till the end, in the end. So we can see that the GCD of whole array A is just 1. So what is f of a? F of a is the count of unique numbers in the prefix GCD. So let's take an example of a right now. That would be better. So a, let's take it would to be 12, then 6, then 4, then 1. So the p array would look like p is the prefix GCD array. So till here the GCD would be 6, 12. Till here the GCD will be 6. Now till here the GCD will become 2, and till here the GCD will become 1. So since these two are not equal and these two are not equal and these two are not equal, the overall score will be 3. So we can say that f of a is the count of unique numbers in the prefix GCD except 1. So we are simply counting all the unique numbers minus 1, right? So we can just exclude this one and we can count these three. So if we take another example, let's take a is equal to 24, then 6, then 12, then 4, and then 3. So p will be 24, 6, 6, then 2, then 1. So obviously, how many distinct elements are there? 24, then 6, then 2, then 1. So answer would be 24 is not equal to 6, 6 is not equal to 2, 2 is not equal to 1. Simply the answer is 3. So 1, 2 and 3 different numbers. So f of a is 3. So that is value of f of a. And answer is simply expectation of f of a, where a can be any array of length infinity and ai is from 1 till n. So how do we find expectation? Expectation. So expectation is kind of like what is the expected value? What is the most probable value of f of a? So how do we calculate this? So this is nothing but, since what we are doing is we are counting the number of distinct numbers in the prefix GCD, right? So count of distinct numbers in prefix GCD, right? That's what we are doing. We are counting distinct numbers in prefix GCD except one. So since we are taking we need to find what is the expected value of count of distinct numbers, right? So to find that, what we can do is we can find the probability of each number appearing in the prefix GCD. Now obviously prefix GCD, the numbers will be from 2 till m, right? We are not counting one because we took the problem as count of distinct numbers in prefix GCD except one. So what we can do is we can find the probability of each number appearing in the prefix GCD from 2 till m. We can, if we find this value, so let's say that uh, let give me some variable. Let's say that capital F of some value x give me probability of x appearing in prefix GCD. So if we know this value for all 2 till m, what will be the expected value of f of a? So expected value of f of a will be nothing but summation of 1 into p of I, where I is equal not p of I, capital F of I, where I is equal to 2 till m. So basically 1 is the contribution of each distinct number, right? And f of I is the probability of each distinct number appearing. So if we take the sum of all that, we'll get the expectation value. So now we somehow need to find f of I. So first of all, let's denote the first number in the array as a1. As a1. A1 is the first number in array. So for I to be a part of prefix GCD, I must be a divisor of a1. Because a1 is a part of every prefix GCD, right? Because it is the first element. So I must be a divisor of a1. Only then I has a chance to be a part of the prefix GCD. Because let's say if a1 is 10 and I am calculating the probability of 7 being a part of the prefix GCD, then obviously it is 0. Since the first element is already 10, so all the further GCDs would be a divisor of 10 only. It cannot be 7. So f of 7 is already 0. So that's why the first important condition is that I must be a divisor of a1. So what we can do is, so f of I, we can write it as probability that I is a divisor of a1. Now again, we can see, let's say that a1 is equal to 10. So let's say that a array is like this: 10 and then 3 and then 1. So prefix array would be 10, 1, 1. And let's say I'm trying to find f of 2. So obviously, even when this array has the first element as 10, it is not necessary that it will contain 2 in its prefix GCD. So this is not the actual probability, right? This is only, we can only say that if the first element is not a multiple of I, then there is no way that I can be a part of the prefix GCD. But if the first element is a multiple of I, then it may or may not be a part of the prefix GCD. So now we need to subtract some of the cases where I is not a part of this thing. I is not a part of prefix GCD. So when can I be not a part of prefix GCD? So let's say that I know a number y which is a multiple of I. So let's say that I do know the value of y being a part of prefix GCD. So f of y is the probability that y is a part of prefix GCD. So let's say that till some ith index we have y equal to the prefix GCD. So the next unique number that we will get in this after this y could be any divisor of y, right? It could be I or it could be not I or not I. So we actually need to subtract the probability when it is not I, right? So when will this be not I? So we can see that if we have a prefix GCD of y and after the next number we are changing this prefix GCD of y to be the k, and k is not a multiple of I. So we need this probability that we had the prefix GCD I and y and it got changed to k, which is not a multiple of I. So this probability we need to minus, because this is the same case that we had a1 is equal to 10, which is a multiple of 2, but on the second number we had 3. So from 10 we directly went to 1 in the prefix GCD. So from y, if we go to some k which is not a multiple of I, then we can say that from further from this k we will never be able to get I as a prefix GCD. So what will be the probability that from this y will go to some k which is not a multiple of I? So first of all, what are the total number of cases where the GCD will change, where the prefix GCD is currently y and after some number it will become some k? So that would be m minus m by y. Because if my current number, let's say p is currently 5, right? So to change this p, I cannot take the next number as a 10 or 15 or 20, because if I take the GCD of 5 with any multiple of 5 only, then my GCD would remain the same, right? So what I'll do is I'll remove all the multiples of y from m. So from 1 till m, I'll remove all the multiples of y, which is m by y. So basically m by y is the number of multiples of y till m. So this is m minus m by y. So these are all the cases where the GCD gets changed from y to some k. Now we need to find the probability that it gets changed to a number which is not a multiple of I. So what we can do is, the favorable cases would be m minus m by I. So here we are removing all the multiples of I. And the total number of cases where we just remove the multiple of y, and the favorable cases are where we remove the multiples of I. So this number actually becomes f of y into m minus m by I upon m minus m by y. And we need to sum this for y equal to multiple of x, multiple of I. Because from every multiple of I, we need to calculate the probability that we go to some number which is not a multiple of I. So this is that probability that we go from y to some number which is not a multiple of I, which is not a multiple of I, right? So this is that probability. And of course this is the probability that y is we have y as a prefix GCD. So if we have y as a prefix GCD, then this is the probability that we will now not have I as a prefix GCD, and this will be the final probability that I is a prefix GCD. I is a element in prefix GCD. So obviously we can see that this becomes a DP, since f of I only depends on numbers greater than I, because y is a multiple of I. So we can write a simple DP over this, and for each I we'll run a for loop from I is equal to 2 till I less than equal to m, and for each I we'll run a for loop on its multiple. So the complexity of this would be n log n, because it would run m by 2 plus m by 3 plus m by 4 and so on times. So this is m 1 by 2 plus 1 by 3 and so on times. So this is m log m. So that way we'll be able to calculate the value of f of I, and then our answer would be simply this. So I'll show you guys the code for this. So this is the code for this. So I'm creating this vector of dp. dp of I is basically capital F of I. So initially capital F of I is this value, basically that ai is a that I is a multiple of a1. So for I to be a multiple of a1, we have m by I favorable choices. So basically, sorry, a1 to be a multiple of I, we have m by I favorable choices, and total choices as m. So we will do m by I upon m as probability of dpi, and then we will subtract this. So when to subtract this, total is m minus m by j, and bad is m minus m by I. So m minus m by j is total, and m minus m by I is bad. So we will do dp of I minus equal to dp of j into bad upon total. So dp of j into bad upon total, and we'll run this for loop for each multiple of I, and once this is completed, we will have calculated all the values from dp2 till dpm. So in the end we can just add all the probabilities, and that would be our final expected value. So if you guys have any doubts in this solution, you can ask. I'll be back in a minute. You guys can ask your doubts till then. So I think you guys don't have any more doubts. I'll wait for another minute. Expected code forces rating of this problem, I think 2000, maybe 19, and more than 1900, definitely 2000. Yeah. This was a very hard problem. Actually, I don't know how so many solved in div 2, but yeah, in div 1 this was pretty hard problem. Like only 60 people solved in div 1, and it was rated till 6 stars today, I think. And the last problem before this was solved by one around 140 people, I think. So yeah, This was a tough problem, and I also didn't solve this during contest. Oh, very hard to reach 5 star now. Yeah, it's a little bit more difficult to increase rating in CodeChef because CodeChef doesn't allow huge changes to your rating. Basically, in CF you can get huge deltas, but in CodeChef after the first few contests, it's quite hard to get huge deltas. So yeah, it's hard. Okay, so I don't think you guys have any more doubts. So I'll end the PCD. Thank you.